Hello everyone, welcome again, and we will continue our learning on simulation. In previous video, we are talking about creating a gas reservoir model using MBAL. By the way, we are still in series of videos about integration between reservoir model using MBAL, well model or well simulation using Prosper, which we are now using, and with production facility or network model or simulation using GAP software. All right. In the previous video, we have constructed a reservoir model using MBAL. We constructed a gas reservoir model. And as I said before, we will produce the gas using 4 wells. Okay. So in this video, we will construct 4 well models to represent 4 wells, and the 4 wells will take the gas from the reservoir, and the gas will be produced through the production facility whose model will be modeled using GAP software, which we will discuss in the next section. Okay, so now we will concentrate only on the well modeling, well simulation using Prosper software, and we will construct yeah, I think it's a typical well without artificial lift, gas well. So it will be quite easy, quite simple. All right, so let's do this. So as you can see, we are now inside the Prosper. In the software, we have this section to show the picture of the well. Okay, and then this is the starting point. This will be section for PVT. This is for the reservoir or the IPR, inflow performance relationship. And this is about the well itself, the construction, the configuration of our well. And this is the list of analysis that we can do. All right. And we open this first. Okay, you can follow me. For the fluid description, fluid, we will select, okay, open the drop-down menu. Right, wait a minute. Dry gas, I mean dry and wet gas. Okay, method black oil, single stage separator, disable warning for PVT warning, water viscosity we will use default correlation, and for the water vapor, open the drop down menu, we will use calculate condensed water vapor. Okay, so there will be water vapor inside our gas, and we will calculate the condensed water vapor. All right. And flow type, tubing flow, well type producer, method none. Okay, you can input the company, field location, well, and so on and so forth, but we will skip them. And also the comments. Okay, yeah, we can type in well A. We will have well A, B, C, and D. Okay, and for the calculation type, predict. Let's say it's an offshore well. Model, rough approximation, the range full system, brine properties default. It is a case hole completion, nose and control, and for the reservoir inflow type, single branch. Okay, we can click done, and we will wait for a while until the Prosper or the system is ready. Okay, wait a minute. All right, yeah, you can see everything is open. Now we go to the next section, PVT section, open this one, PVT input data. Okay, so you can follow me for the gas gravity 0.77, separator pressure at this pressure, and let's say the condensate gas ratio 22.2, and the condensed gravity 67. with water gas ratio of 1, water salinity 100,000. It is similar with the data that we use in the MBAL model. Okay, so you can open again the MBAL video and you can cross-check the data. Okay, so the water salinity 100,000 ppm, H to S0, and then for the mole percent of carbon dioxide 0.37, and for the nitrogen it will be 4%. Gas viscosity we will use Lee et al. And as you can see, for the other data, water viscosity, we will use correlation, water vapor, calculate condensed water vapor. Okay. Reservoir data, reservoir temperature 166 and the reservoir pressure 5,300. Water vapor data, automatically populated the data 0.27 minimum water gas ratio, and we can open the water vapor plot by clicking this button. Yeah, you can see the plot of saturation WGR versus pressure. Okay. It is very important, right, for gas well, especially water gas ratio, including the water from the condensed water. It is important. So of course we need to model it. Okay. And then click done. Okay. And then for, yeah, we need to do matching here, just like what we did in MBAL software. So open the match data. Here we will do the matching, match data. All right. Just like before, we only have 2 points. The reservoir temperature is 166. And the point is like this, the pressure, Z factor, gas viscosity, gas formation volume factor, and for the second pressure, okay, the Z factor, gas viscosity, and for the gas formation volume factor. Check again the unit, PSIG for the pressure, gas viscosity for the centipoise, centipoise for the gas viscosity, and gas formation volume factor, cubic foot divided by standard cubic foot. All right, so far so good. And now we can click match. Match all. Be careful here. Let's see what will happen. We have 2 points here, the real data, and the red line is actually the correlation results. Let's check it out if we click this button. By the way, we can check also the gas viscosity by clicking this button. You see, they don't match, right? The actual data, the 2 black points, the red line is Lee et al., the blue line is Carr et al. And for the gas formation volume factor, it's quite matched already. But we still haven't done any matching. So let's check it out. Click this button, match all. If I click this button, match all, the Prosper will do the matching. Okay, let's check it out. Okay, so now you can see the Prosper matches our data with the correlations. So for the Z factor, it's very good actually. For the gas viscosity, very good, right? And for the gas formation volume factor, also the matching is very good. Even better than what we get in MBAL software, all right? And to select the best correlation, let's check the statistics. First, for the Z factor and gas formation volume factor, we don't have any selection, okay? We can only take it. For Z vector, parameter 1 is quite close with 1, so okay. Parameter 2 is close to 0, so it's okay. Standard deviation, e to the power of minus 8, which is very small, so it's satisfactory. It's good. Gas formation volume factor 1.077, quite close with 1. Parameter 2 minus 0.000, very close to 0, so it's good. And for the standard deviation 7.2504 e to the power of minus 5, which means times 10 to the power of minus 5, which is very good. Okay. And for the gas viscosity, Lee et al. Has parameter 1 closer to 0. All right, compared to Carr et al. Because Lee et al. Is 1.066, whereas for Carr et al. Is 1.6. And for parameter 2, Lee et al. Is closer to 0 because it is 0.000, whereas Carr et al. It is minus 0.007. Okay, so for parameter 2, Lee et al. Is better than Carr et al. And for the standard deviation, these two equations have the same standard deviation. So in conclusion, Lee et al. Is better than Carr et al. All right, just like what we get in MBAL software. Okay, Lee et al. Is better than Carr et al. So we will select Lee et al. As our correlation. Yeah, you can check the parameters by clicking this button. The same result actually, like what we have here. Done. And also create the plot or plot all, like this one. Exactly what we have in this small section. Okay, we can get or we can plot the Z vector, gas viscosity, okay, gas formation volume factor, and also gas density. Click done, done, done. You see the sign, PVT is matched, which is good. And we will select gas viscosity correlation Lee et al. Instead of opening this drop-down menu, instead of Carr et al. We select Lee et al. Click done. And now we go to the next section, which is IPR, Inflow Performance Relationship. Open this button. To model the IPR, we select Petroleum Experts correlation. Okay. It's a proprietary correlation or equation or model owned by petroleum experts. Okay, so yeah, we can use it. It's quite good. And for the skin, we will model it using Caracas and Tarik equation. Whereas for the deviation and partial penetration skin, we will use Chincho 2 Martin Bronze. Okay. And the reservoir data, reservoir pressure is 5,300, automatically populated. Okay. Just we just want to check it. Reservoir temperature is 166. Okay. Water gas ratio is 1. Condensate gas ratio is 22.2. Stock tank barrel per million standard cubic feet. Okay. Or foot. All right. Now we need to input data for the reservoir model. So reservoir permeability 25 millidarcies, reservoir thickness 120 in feet, drainage area 420 acres, DH shape factor 31.6, assuming circular reservoir, wellbore radius 0.354, perforation interval 75 feet, time since production started, so it's a transient model. Let's assume 75 days with reservoir porosity 0.5, I mean 0.15, conduct water saturation 0.25. Okay, for the non-Darcy flow factor, D will be calculated. Beta factor method original. Permeability entered is total permeability. Okay, and now we need to input the mechanical and geometrical skin. Okay, reservoir permeability 25, shot density 8, perforation diameter 2 inches, perforation length 4 inches, perforation efficiency assuming 1, damage zone thickness 6 inches, damage zone permeability 8 millidarcies, crack zone thickness 0.5, crack zone permeability 4. So yeah, you can see the model, the Caracas Tarik model is very detailed. Okay, so yeah, we can use it, we can follow it. In this case, we need to provide this thickness, the damage zone permeability, crack zone thickness, crack zone permeability. We need to provide that data into the Prosper model. Shot facing for the perforation. Okay, so the mechanical geometrical skin will consider the perforation configuration. All right, this equation by Caracas Tarik. So for the shot facing of the perforation is, let's assume 120 degrees, wellbore radius 0.354, and vertical permeability 2.5 millidarcies. Okay. And for the deviation and partial penetration skin, deviation assuming 0, penetration 1, 100%. Okay. So all the thickness of the reservoir 120 will be open, will be penetrated. Okay. And then for the vertical permeability, 2.5 millidarcies. Okay, so now click calculate. And by clicking calculate, you get the non-Darcy flow factor and also this AOF, or absolute open flow or maximum flow rate. Okay, so far so good. And we can construct the IPR, plot results, plot the rate in x-axis, and plot the pressure on y-axis. Click done. Let's wait. All right, so this is our IPR. You can check the skin 7.14, the total skin, with perforation skin is 5.27 and damage skin is 1.87. So if you combine the perforation skin and damage skin, you will get total skin of 7.14. And the absolute open flow is 145.989, or yeah, basically the LF 146 million standard cubic feet per day. Okay, this is the main results. Click finish, click done, click done. So we have completed the IPR section, and now we need to construct the mechanical aspect of the well by clicking this section. input data, deviation survey, downhole equipment, and also let's check the geothermal gradient and also the average heat capacities. Click edit. Okay, so now you can follow me for the deviation survey, the trajectory of our well. Okay. Yeah, actually it's a deviated well, but in the IPR section, we input the deviation is 0. That's okay, because basically what we did in that section, we want to calculate the skin due to deviation. And yeah, let's neglect that. It will not be very big. Okay, so we input 0 just to make the skin factor quite conservative. Okay. And then this one. Okay. Okay. 4140, 5000, 4560, 5400, 4900. All right, this is our trajectory. You can plot. Okay, we have a vertical section here and deviated section here. Okay, click finish and also click done. Now we need to construct the downhole equipment starting from Christmas tree at 0 depth. And then we have tubing down to 1000 feet with tubing ID inside diameter this one. We use default roughness. And then we have subsurface safety valve inside diameter of 3 inches. And then tubing again. Okay. Open the drop-down menu down to 5000 feet with the same ID with this. And lastly, we have casing. From the top of the well down to 5400 with casing inside diameter of 6 inches, and we can use the same roughness. Rate multiplier 1. Okay. And then we click done. Now we need to input the geothermal gradient. Okay. 45 degrees Fahrenheit, 75 degrees Fahrenheit. And at the reservoir depth, let's say 122. I mean at this depth, 5400. Okay. Click done. And we can use the default numbers for average heat capacities. Click done. We can check the summary by clicking this button. All right. In table, we can also draw. You can see this is the configuration of our well. Starting from Christmas tree, tubing, we have safety valve, tubing down to this depth, 5000. And we have casing. Okay. Yeah, the casing in reality should be from the top. Okay. But of course, this diameter is not, yeah, it not necessarily starting from the top, because on the top we usually have surface casing, conductor casing, right? This is for the production casing, whose tubing inside diameter, I mean, whose inside diameter is 6 inches. All right, click done, done, done. So far, so good. So let's wait for a while. All right, so this is the well sketch, the well configuration. It means we are now ready to perform the nodal analysis or the simulation. Okay, click calculation, system, IPR VLP, and let's assume the wellhead pressure, the top node pressure is 2100 with water gas ratio of 6 and condensate gas ratio of 22.2. Later on, the wellhead pressure will be based on the gap, not based on the prosper. Okay, so now in this section, we just want to do the calculation for, yeah, for our interest. And then for the solution at bottom node, rate method, yeah, we can use this. For the vertical lift correlation, yeah, we can use petroleum experts too. All right, all good. We can click calculate, show calculating data. Okay, we get the nodal analysis, the IPR, the red line, and also the VLP, the blue line. We can check the plot here, or we can also check the plot by clicking this button, plot, system plot, plot all cases, x-axis, the gas rate, y-axis, the vertical axis, VLP and IPR. Click done. All right, so this is our nodal analysis. Okay, so we have constructed one well. Later on, this well will be connected to the embal, to the reservoir in the gap. Okay, so now we need to construct 3 more wells, but basically they are typical. So I will just copy this model and paste it for 3 times. So I have well 1, 2, 3, and 4. And then for the well 2, 3, and 4, I will just change the properties, change the parameters, but basically they will be typical. Okay, so we can get 4 wells, and in the next section we will connect 3 wells. I mean, we can connect 4 wells with the gap, which is the production or network software, production network modeling software. Okay, so we can save this model and we can copy it 3 times, and we can have 4 well models, which are typical. Okay, so I'm just going to, okay, so this is the first well, well 1, and I will just start from this file, this well 1, and I will do some modifications and save it as well 2. Okay, so now we will use well 1. Okay, we will keep many data. Okay, we will keep the majority of this configuration, and we can change few parameters and then save the file as well too. Okay, so let me check. Okay, everything will be kept. All right, click done. And then for the PVT, everything will be kept. All right, already match. Click done. And then for the, yeah, let me check again. Okay, water gas ratio. Yeah, I will. Yeah, we should keep it. We must keep it. Yeah, you see, this is actually well 1 Eng-Man, but I will save it as well to Eng-Man. Okay, so I just use the first file, okay, to make my life easier. Click done. And then for the IPR, okay, The same reservoir pressure, temperature. Okay. The same reservoir permeability. But let's assume in this second well, the reservoir thickness is only 50 feet. Okay. So the thickness of the reservoir is not uniform. Some thicker, some thinner. Okay. So let's say it is thinner in well 2 with, okay, drainage area of 500, the same wellbore radius, perforation interval, let's assume, yeah, 100% of the reservoir thickness will be perforated. So the perforation interval is 50. Time since production started, 1. Porosity, 15%. Connaught water saturation, 25%. Okay. And then for the mechanical geometrical, reservoir permeability the same, density, shot density 8. Perforation diameter in this well, let's assume 2.5 inches. Perforation length 4. Perforation efficiency 1. Damage zone thickness, damage zone permeability 12. Crack zone thickness, yes. Crack zone permeability 8. Shot facing, okay. Wellbore radius, okay. Vertical permeability 2.5, okay. That's good. In the section, the same. Now we can calculate. Okay. Or I can leave it blank first if I can, or not. Okay, already calculated. All right, in this well, the AOF is smaller compared to the first well. The AOF is only 92.5 million standard cubic feet per day. So you can check the results. Click done. This is the IPR. Okay, the skin, perforation skin, damage skin, the absolute open flow. Okay, click finish, finish, finish. Yeah, at this point we can save this file first and call it well2. Okay, I will do that. Okay, so now we are now well2. Actually, I have saved it as well2. Okay, I will do the same. Edit. Let's check the trajectory. Okay, the trajectory, let me check my data, the same. Okay, we can keep the same trajectory. And then for the tubing or the well configuration, yeah, the same. Click done. The temperature should be the same, and default heat capacities. Okay, click done. Click done. Now for the nodal analysis, click calculation, system IPR and VLP. Let's say the top node pressure, the wellhead pressure is 430. And yeah, we can calculate. All right. So the top node pressure here is smaller, just to check it, because later on the wellhead pressure will be based on the gap. Okay, by lowering or by having lower top node pressure, of course, we can increase the gas rate. That's why we have the intersection between, or the intersection between IPR and VLP at this far right side. And we can produce at rate of 70.7 million standard cubic feet per day, which is very big. Okay, so again, you can check the plot, system plot all cases. done. Yeah, this is our second well, the nodal analysis for second well. Click finish, finish, save. Okay, so we have completed the second well. I will start using this second well. Okay, and then I will name it as well 3, and I will do some modifications. Okay, I will pause for a while. Okay, so now we are in the third well. Okay, I use the file from well 2. Okay, or I can also use the file from well 1 and do some modifications and call it well 3. Okay, let's do some modifications. Okay, let me check this section first. Okay, everything is good. No problem here. Okay, click done. And also the PVT. Okay, let's check the IPR. Let's say the reservoir thickness here is 70 feet with drainage area of 500. Okay, the same. Perforation interval 70 feet. All the thickness of the reservoir is perforated. So 70 feet. Time since production start at 1. Reservoir porosity 0.15. Connaught water saturation 0.25. Okay, the non-direct flow factor will be calculated. Check the mechanical geometrical skin. Shot density 8, perforation diameter 2.5. Now the perforation length is 6 inches. Damage zone thickness of perforation length, yeah, 6 inches. Damage zone thickness 8 inches with damage zone permeability 12 millidarcies. Crush zone thickness 0.5. Crush zone permeability here is 12. Shot facing 120. The same wellbore radius, vertical permeability 2.5. Okay. And again, we can keep it like this one. Calculate. Okay. Now we get higher AOF, higher absolute open flow compared to the previous one. The second well, the well 2, has absolute open flow around 90, if I'm not mistaken. But now the third well has AOF of 139 million standard cubic feet per day. Plot results, click done. Okay. Finish, done, done. Let's check the trajectory, check the downhole equipment, check the geothermal gradient, edit. Okay, I will maintain the trajectory the same. Done. Check the downhole equipment. Exactly the same. Yeah, in reality, they should be different between one well and another well. But yeah, for the sake of example, okay, we will copy or we will have the same, exactly the same well configuration. So no problem there. Okay, done. Check the summary if you want. Draw downhole. Okay, done, done, done. All right. For the sake of completeness, we can do nodal analysis system IPR VLP with, for example, the wellhead pressure 700, top note pressure. Let's assume water gas ratio of 1, and we can click calculate, show calculating data. Be careful. The second well has operating gas rate of 70 million standard cubic feet per day with wellhead pressure 400, right? 430 PSIG. Now, what will happen if we have higher top note pressure of 700? Calculate, show calculating data. Okay, we can get higher operating rate of 92. Do you know why? Because now we have, or we assume, smaller water gas ratio of 1. Previously, we have 6, which make the flow heavier. Now the water gas ratio is smaller. That's why we will have operating gas rate higher, 92. What will happen if we have the same water gas ratio as the previous case of 6? Calculate, show calculating data. Yeah, the water gas rate, I mean the operating gas rate is actually smaller only, but still higher than the second well. Okay, here we have 91. Why? Yeah, because basically the IPR, the absolute open flow, the reservoir influx for the second or for the third well is better, all right, compared to the second case. Okay, so I think we can go back to water gas ratio of 1, calculate, show calculating data. Okay, done, and save it as well tree. Yes. All right. Lastly, we can file, save as well4. Okay. Okay, so now this file is well4. Save. You can see well4. Yes. All right. And check this one. That should be the same. Done. Same PVT. Okay, same PVT. Well4 Eng-Man. Done. The IPR should be the same or should be different. Now the reservoir thickness is 80 feet. Drainage area smaller, only 300 acres. And also the perforation interval 80 feet. All the thickness of the reservoir is perforated. Okay. And for the mechanical geometrical skin, 25, 6, 2.5, perforation length 8, perforation efficiency 1, damage zone thickness 6 inches, damage zone permeability 12 millidarcies, crash zone thickness 0.5, crash zone permeability 6 millidarcies, shot facing 120, wellbore radius 0.354, vertical permeability 2.5. Keep the deviation and partial penetration skin. Yeah, you can check this number. This number will be changed if I click calculate. All right, there. And now the absolute open flow is 162 million standard cubic feet per day. Okay. Click plot results. Done. This is the IPR. Okay. the IOF, skin, and perforation skin. Finish. Done. Let me check again for the mechanical and geometrical skin. This, okay, 8. All right. Okay. Okay. So now click done. Now check the well configuration, deviation survey, downhole equipment, geothermal gradient, edit. Again, the trajectory is the same. You can check again the plot, the same trajectory. Finish, done, the same well configuration, and the same geothermal gradient. So very easy, right? Done, done. Okay, lastly, calculation, nodal analysis, system IPR and VLP. Let's check if we have high wellhead pressure of 1000 psig. Click calculate, show calculating data. Yeah, although we have high top node pressure or high wellhead pressure or high back pressure, but we can still operate at high gas rate of 99 because basically we have good influx. The reservoir performance, the IPR is good. So that's why we have the intersection between IPR and VLP quite high, which gave us operating gas rate at 99 million standard cubic feet per day. Okay, you can plot, system plot all cases, done. Okay, so far so good. So we have constructed 4 wells. To make sure, click save. Okay, so in the previous video, we have constructed the reservoir using MBL software. In this video, we constructed 4 wells, which are typical, but they have different IPRs. Okay, we have constructed 4 wells, and the 4 wells will produce the gas from the reservoir. So we will connect the reservoir with these 4 wells, and then connect the 4 wells with the production facility, production network. And the network, the system will be modeled, will be simulated using GAP software, GAP, GAP, and we will discuss about GAP software in the next section. Okay, so see you again.